So hello guys, today we are going to see two-dimensional analysis of blood flow post-stent development using COMSOL software. So in COMSOL software, the study was chosen as time-dependent, which follows the Navier-Stokes equation, and the blood flow is chosen as laminar flow. Okay, laminar flow, and here we have just assumed that the blood flow is incompressible flow and the density was taken as 1060 kg per meter cube and the blood viscosity was chosen as 0.004 pascal second. So this is the geometry of stent strut as you can see here. So we have just made this design in SolidWorks. Okay, so for the strut shape optimization we have just flattened the edges of the rectangular shaped strut as 0.05 millimeter. So as you can see here we have just flattened the edges. So for performing the laminar study, or you can say the blood flow study, so what are the boundary conditions we have used? So we have just selected the top of the rectangle as inlet and the base as the outlet. Okay, and no slip condition has been considered for the arterial wall in the boundary with the stent. So at the inlet we have just taken the flow velocity as 0.25 multiplication with f. So f is representing here is frequency, and we can say f as pulsatile equation. So you can see here this equation, so which we are going to insert in the COMSOL software. So these are the boundary conditions which showing the actual thing. Like at the inlet we have just selected the top. Okay, and for the outlet we have just selected the base. So this is the mesh geometry. We have just used the extremely fine mesh. So after performing all of the things, so we got these results. These are the surface plot, you can say, of velocity. So here you can see the maximum velocity is 0.8 meter per second. Okay, so now we are going to perform this study in COMSOL software. So this is the stent strut geometry as you can see here. So we have just imported from SolidWorks, and first of all we have to define the parameters. In the parameter section we have just defined the time as 0 second, and for inserting the pulsatile velocity you have to just right click on global definition and then function and then click on piecewise. Okay, then this function, like you can say, this will open. So you have to write the label as f and the function name as f. So in the argument you have to just type t, because in the parameter section we have defined the t, that's why. So and in the intervals we have to just give the start at 0 and end at as 0.5 and function is sin pi t, and second function we have to give 1.5 minus 0.5 multiply cos 2 pi t minus 0.5. Okay, so then in the laminar flow section we have to give the fluid properties. So as we have already discussed that the density we have taken is 1060 kg per meter cube and the dynamic viscosity is 0.004 pascal second. So in the wall we have just taken the no slip condition, and for taking the inlet and outlet in that section, so you have to just right click on laminar flow, then you will find that there is inlet option, you have to just click on it. Okay, so in the inlet you have to just select the top of the rectangle strut. Okay, so here you have to give the normal inflow velocity as 0.25 multiplication with ft. So ft we have already defined as you can see here. Okay, so and for the outlet we have to just select the base of the strut. Okay, So here will be the pressure 0, and then we have to do the massing. For we have used the element sizes extremely fine, and then just clicked on build all. Okay, and for computing the result you have to just go in the study section and just compute. Okay, so it will take some time, okay, to compute. Finally we got surface plot for velocity. Okay, so as you can see here, the maximum velocity is 0.8 meter per second. Okay, and the pressure is also here. Okay, so this is the final result, as you can see in the conversion plot.